Hey everyone, today I want to walk you through one of my favorite problems from this year's EMO, held on the Sunshine Coast, a problem called sunny lines. It looks intimidating at first glance, but the idea behind it is genuinely elegant once you see it. Let's get into it. Here's the problem, word for word. A line is called sunny if it's not parallel to the x-axis, not parallel to the y-axis, and not parallel to the line x plus y equals 0. Now, take some integer n, at least 3. We want n different lines that together cover every point with positive whole number coordinates a and b, where a plus b is at most n plus 1. And the question is, out of those n lines, exactly how many of them, call that number k, can be sunny? Let's slow down and unpack. Sunny. It just means the line's slope avoids three specific values: 0, undefined, and -1. Simple enough on its own. But here's what makes this problem sneaky. We've got roughly n squared over 2 points to cover, using only n lines. That's a lot of pressure per line. And slanted, sunny lines turn out to be worse at covering points than lines running in those three special directions. That imbalance is the whole key to this problem. It's what's going to squeeze k down to just a few possible values. Picture the points we need to cover. They form a triangle. 1 dot on top, 2 below it, 3 below that, and so on, down to n dots on the bottom row. This triangle has 3 sides. The left side sits on the line x equals 1. The bottom sits on y equals 1. And the long diagonal sits on x plus y equals n plus 1. Here's the beautiful part. Those 3 sides are exactly the 3 forbidden, non-sunny directions. That's not a coincidence, it's the heart of the whole problem. Here's the one geometric fact that unlocks everything. Since our triangle is convex, any line can cross its boundary at most twice, unless that line lies exactly on top of one of the 3 sides. In that special case, instead of just clipping through, it swallows an entire side at once, all n points in one shot. And since those 3 sides are the forbidden directions, that swallowing line is automatically non-sunny. Let's count. The triangle's boundary has 3n-3 points on it in total. If none of our lines lies exactly on a side, each line can grab at most 2 boundary points, so all n lines together cover at most 2 n points. But we need 3n-3. And 2n only beats that when n is 3 or smaller. So for any n bigger than 3, we're forced, not by choice, the math forces it, to use at least one line that lies exactly on a side. So what happens once we're forced to use one of those side lines? Well, it's automatically non-sunny, so removing it from our count doesn't change k at all. And once it's gone, the remaining n-1 lines just have to cover the next triangle down, the one for n-1. That's literally the same problem, one size smaller. So no matter how big n starts out, this keeps shrinking down until we land on n equals 3. That's where all the real work happens. Let's zoom into n equals 3. There are just 6 points here, and I've labeled them A through F. If you check every single pair among these 6 points, only 3 pairs actually have a sunny slope: A paired with E, B paired with F, and C paired with D. And here's something cool, these 3 pairs use all 6 points exactly once. It's a perfect matching. Now let's actually build examples for each value of k. For k equals 0, just take 3 vertical lines, x equals 1, x equals 2, and x equals 3, none of them sunny. For k equals 1, take 2 of those vertical lines, x equals 1 and x equals 2, then add one sunny line, y equals x minus 2, 2. Cover the last leftover point. And for k equals 3, use the 3 sunny pairs we just found, the line through A and E, the line through C and D, and the line through B and F. All 3 are sunny, and together they cover everything. So why can't we land exactly on k equals 2? There are only 2 possibilities, and both fail. First, if one of our lines is a full side of the triangle, that leaves 3 points behind, but every possible pair among those 3 points turns out to be non-sunny, so we're forced to add a second non-sunny line, which breaks our count. Second, if we don't use a full side at all, each of the 3 lines has to cover exactly 2 points, with no overlaps. To get 2 sunny lines, we'd need to pick 2 of our 3 special pairs, but that automatically drags in the third pair too. You just can't stop at 2. It always snaps to 3. Just to double check ourselves, here's a completely independent argument for why k can't be bigger than 3 either. Shrink down to the tightest triangle where k sunny lines might still work. Each of its 3 sides needs at least k points covered, so across all three sides, that's at least 3 k points needed in total. But each sunny line can only ever reach 2 boundary points, so k sunny lines can cover at most about 2k plus 3 points, even being generous about shared corners. And 2k plus 3 is always less than 3k once k gets bigger than 3. The numbers simply don't work out, so k can't exceed 3. So, putting it all together, the only possible values are k equals 0, 1, or 3, and that holds for every single n, 3 and up. We got there two ways: by shrinking every larger case down to n equals 3 through induction, and by directly counting why anything outside 0, 1, and 3 just doesn't add up. That's the complete proof. Thanks for following along.